Now let's state a couple properties of inverses. If we have a function and we want to find the inverse of it from its graph, we reflect the line or the graph across the line y is equal to x. In other words, if a comma b is on f of x, then b comma a is on the graph of the inverse. Let's try this out on this first, or on each of these examples. Notice how this given graph goes through -2, 0 as an x-intercept and 0, 4 as a y-intercept. Let's reverse those points around. Let's go, instead of -2, 0, let's go with 0, -2. And instead of 0, 4, let's go with the point 4, 0. When we graph that line, we now have a diagonal line right there. And it turns out that this graph is a reflection across the diagonal line y equals x. All functions and their inverses will be reflections across that diagonal line y equals x. Now, this inverse is also a function because it obeys the vertical line test. Both f and its inverse are functions, and so we have f of x and f inverse of x. If, however, the inverse is not a function, we can't call it f inverse of x. In that case, we need to call it just a relation instead. Let's do the same thing on this curve. Notice that this function is not invertible. Its inverse will not be a function because this fails the horizontal line test, meaning the inverse will fail the vertical line test. Now I noticed that down here at the bottom left, this node point is at -3, -3, and if you reverse those two numbers around, you get the same value. An x-intercept appears to be about -1 1/3. We're going to switch that to a y-intercept of -1 1/3. We have a y-intercept of about 1 1/2. We'll get an x-intercept of about 1 1/2. And both of these seem to go through 3, 3. So if I join those points and kind of continue that on, we will have this drawn out for us. And notice that if we draw in the line y equals x, we have a mirror image, we have symmetry on both sides of that line also. What we were just dealing with was finding the inverse of a graph from its graph. Now we want to find the inverse of a function from its equation. And there's basically two steps: switching the x and y, and then solving for what I'm calling the new y. So here we go. Let's try this on a problem. We have y equals 2x cubed minus 5. I changed the m of x into a y. Now I'm going to switch the x and the y. That will give us x is equal to 2y cubed minus 5. Now our goal from here on out is to solve for the new y after we've done that switch. So we want to get the y by itself. First thing we're going to do to each side is add 5. X plus 5 will equal 2y cubed. Then we will divide each side by 2. Y cubed will equal x plus 5 all over 2. And then we will cube root each side, and I'm going to switch sides of the equations here, and we will have y equals the cube root of x plus 5 over 2. Now, that is the equation of the inverse, and if it turns out that it is a function, we would then label this m inverse of x. Now, we know that a cubic function generally has this shape right here, and it passes both the horizontal line test and the vertical line test, meaning that this inverse will also be a function. So therefore we can use that m inverse of x notation.